Hello, hello, hello. This is Nicholas, and because of one of my friend's comments that he was doing limits in his calculus class, like the limit as x approaches -2 of x, and he was just getting -2, and he was saying, well, that's very underwhelming, basically, and he's basically like, bruh. So what I said was, well, let's spice things up a little bit, and so let's actually prove limits like this are actually turning out to be this way. In other words, that if you've got a continuous function, you can just substitute in to the limit and get your answer. We're going to go a step further. We're going to actually rigorously prove this. So to start, I would like to actually just write down the epsilon delta definition of the limit. So just remember from the very beginning, this is how we define the limit to be. We said that the limit as x approaches a of f of x is equal to L if for all, that's what this upside down a means, for all epsilon greater than 0, there exists, that's what that sideways e means, there exists a delta greater than 0 such that 0 is less than the absolute value of x minus a is less than delta, implies that the absolute value of f of x minus L is less than epsilon. Okay, so now we have that definition. Maybe take a moment to kind of meditate on what that means, I guess, or go back to my very first video on Calc 1, and I will explain what that means. So now we're going to actually be proving limits with this definition. So the first limit that we'll start out with is the limit as x approaches 4 of 5x minus 7 equals 13. And, well, you'd say, well, I just plug in 4 in for x, and I get 5 times 4 minus 7, and I get 13, and then I'm done. No. We want to do better than that, right? We want to actually prove that you can directly substitute in. And so we're going to prove it using this definition here. So how am I going to start? I'm going to start with some kind of preliminary work, some getting the feel for how this proof would actually look like, and then I'm going to write down what the actual proof, if like you had an exam or something that said prove this, what your actual proof would look like or what that answer would be. So for some like preliminary work, let's just start out with this part here of the definition. We have that the absolute value of x minus L is less than epsilon. And for our specific limit, that is saying that the absolute value of 5x minus 7 minus L, our answer, so 13, is less than epsilon. So, and then that means that we have 5x minus 20 is less than epsilon. Since 5 is a constant, we can factor it outside the absolute value. And we get 5 times the absolute value of x minus 4 is less than epsilon. And from there, we would get that the absolute value of x minus 4 is less than epsilon over 5. Now notice that what I did here was very purposeful because, see, what I wanted to go is I'm kind of working backwards here. And working backwards is not how you do mathematical proofs, but it wouldn't be as instructive of a video if I didn't actually show you the backwards thinking before I actually did the formal proof. So what I did is I started with this definition, and I am working from here back to here. So I want this f of x minus L to go back to this x minus a. And so that's exactly what I have. I have this f of x minus L, that's this, and then I have, in the end, see, my limit is approaching 4, so that's like my a right here. So this x minus 4 is exactly fitting this part right here of the limit definition. And just by direct comparison, if I have this epsilon over 5 and this delta, and I have this absolute value of x minus 4, and this absolute value of x minus 4, and this absolute value of x minus 4, then direct comparison would tell me that I should let delta be equal to epsilon over 5, because these are both x minus 4s, and we have a delta here, and we have an epsilon over 5 here. And so now this is the preliminary work in our step, is actually choosing what we want our delta to be. So I'm going to draw a red bar, and then this is going to actually start the rigorous proof. So we're first going to start, and we're gonna write that we have suppose there exists an epsilon greater than 0. So epsilon greater than 0 is given, and this is always the first line of any epsilon delta proof, and it indicates that our argument is going to work for every epsilon greater than 0. And so now we're going to say let delta be equal to epsilon over 5. And so since the definition of the limit claims that a delta exists, right? There exists some delta greater than 0, then we have to give a value for delta. And that value that we give for delta is the epsilon over 5 that we found right here. So now what we can say is that, maybe just kind of as a side note, since we have epsilon being greater than 0, then that means that delta 2 has to be greater than 0. Now, from this part of the definition here, we have to show that 0 less than the absolute value of x minus a less than delta implies f of x minus l is less than epsilon. And if we can show that, then we've shown that the limit as x approaches a of f of x equals l by definition. So now what we can do is we can say, well, plugging what we have here into this, we have 0 is less than the absolute value of x minus 4 is less than delta, which implies that, absolute value, which implies that 0 is less than not less than or equal to, is just less than the absolute value of x minus 4. And now what is delta? Well, it's epsilon over 5. And so now we can say, well, let's just kind of ignore the greater than 0 for now. We know it's there. So we have the absolute value of x minus 4 is less than epsilon over 5. We can now multiply by this 5, and we can put it inside the absolute value since 5 is a positive constant. And so we'd get the absolute value of 5x minus 20 is less than epsilon, which we could break up into, we want f of x minus l. So we want a 5x minus 7 minus a 13. And we can break it up into exactly that. So that tells us that the absolute value of 5x minus 7, or our f of x, minus our l, our 13, is less than our epsilon. And that's okay because negative 20 is negative 7 minus 13. And so since this here, or really since this here implies this here, then we have proven that the limit as x approaches 4 of 5x minus 7 is indeed 13.